Welcome to the machine learning seminar today. Welcome also to all people joining online. Today's speaker is Professor Albert Bifet, coming from Hamilton today. Albert is director at the AI Institute of the Waikato University and also co-chair of the AIRA, the Artificial Intelligence Researchers Association here in New Zealand. Your interests are mainly artificial intelligence, of course, but big data science as well, and machine learning for data streams. You published a book around that topic, and you are also co-leading different open source projects such as the MOA and SAMOA and StreamDM for Spark streaming. And last year, you also won Best Paper Award, the ACM Conference, which is great. And just recently, you had also the role as co-chair at the ECML, right? ECML-PKDD in Lithuania. And today we will hear about TAIAO. Am I pronouncing that right?
That's good.
Almost.
Yeah.
Yeah, looking forward to this. It's an environmental data science project, and you are leading this project, right? Yep. And yeah, so we will leave it with you.
Thanks.
Thanks.
Thanks for the invitation. We are very happy to talk about Green AI and this specific project, TAIAO. This is this environmental data science project that we have. That's a 7-year project, and yeah, I'd like to give details on the talk. So first thing is that Aotearoa is really well known for the greenness, right? So it's something that internationally, if you ask about New Zealand, everybody thinks about how green is the country. So I think this is one of the characteristics that we have. At the same time, so this is why it's very important to focus on the environment and how we should.
Just wanted to quickly close these things and have it all back.
Yes.
It's also not disappearing. You just unmute it, move it up.
Yeah.
Okay. Sorry for the
interruption. So yeah, so that's the environment part. So this is really, really important. But also at the same time, when we think about green AI, we need to talk about how we the resources that we use, right? So how much resources we are using, and especially how much we are going to use. So this is this idea of Andrew Kaparthi that basically with large language models, what we are doing is building like meta computers that are able to be programmed in English instead of being programmed in programming languages, right? So the idea then is that, yeah, instead of having the traditional CPUs with input, output, so now we are going to have these meta computers that, yeah, the large language models is the one that is going to be doing all operations. And then instead of using Python or Java, we are going to be able to use these prompts. And so, yeah, all of this is very nice, but yeah, this is something we will need to see how we affect the number of resources that we are going to give, especially the energy. And yeah, also I think it's quite relevant to New Zealand because there is this number 8-wire mentality, right? And kiwis are famous for that, right? On how to do things in a creative, innovative way using a small amount of resources. So I think this is also something very, very crucial in terms of how we can do green AI, how we can do that using less resources. So what I'm going to do today is, yeah, basically explain a little bit what is green AI, and then just green AI could be seen as 2 things, right? One is how we solve sustainable problems, and the second one is how we do machine learning AI using less resources. So yeah, so that's the agenda. Yeah, so just starting. So what is green AI? there are many definitions of AI. I really like these ones from the European Commission that says that AI is the combination of technologies that are based on data, algorithms, and computing power, right? And I really like that because it helps us to understand what is AI and what is not AI. No, so basically now it's based on data. So data is the yes, please.
So that just says that that's true of it. It doesn't say as a definition. And I'd say as a definition it's absurd. But continue. Sorry.
Okay. Sorry, what do you mean? It's not a definition.
It's simply put, it is a collection of technologies that do those things. That's merely a description of some attributes of it. It's not. I don't think it can be reasonably read as an attempt at a definition of AI.
Okay. Well, I think if it's how we make a definition, right? We should mention something is.
AI is any collection of technologies that combine, for example, would be a way of making it into a definition.
Okay, yeah, we're gonna have this discussion later, but yeah, I think it's one definition. There are many definitions, so it's or at least it's a way to state it. Yeah, I think it's personally I like this one because it's quite simple and allow us to understand that data and computing power are really the core, right? And we are talking right now about AI because data and computing power is really something that we didn't have 10 years ago. So yeah, I think data is the core, and why the AI systems right now are so powerful is because we have much more data to train the models than before, right? And that's something that we can see. This is a chart of the data that we are using to train the models. So what we see is that if we will have like a logarithmic scale, so still we see that the number of data points that we are using is really increasing in an exponential way. And again, we have computing power, right? And here, again, the number of computation power that we are using, it's now it's doubling every 6 months, and it used to double every 20 months. So this is the amount of computing that we are using to train these models. So this is something that is allowing us to have really powerful models that we didn't have maybe 10 years ago because we didn't have the data and we didn't have the computational power. One issue with that could be that, of course, means that we are using a lot of energy. And yeah, this is something that is maybe something we were not thinking before, but this is something that people start to be aware of that and thinking of, well, so every time we do a query to a large language models, we are using more energy than, for example, using a browser, right? So if we asking ChatGPT could be 10 times more expensive than asking Google. So these are the things that are there. And this is why I think it's really interesting, all of this research that we are having on trying to make these models much more efficient in terms of energy. So I'll start talking about the TAIAO project. This is the project for environmental for solving environmental challenges, and then we'll talk about one approach to do green AI. So the TAIAO project is this environmental data science project. This is a project of 7 years funded by MBIE with University of Waikato, Auckland, Canterbury, Becca University of Wellington, Victoria University of Wellington, Becca, and MedService. And yeah, the idea is really having a data science environmental program where we try to see how we can help environmental scientists to deal with all of these problems. And yeah, so as you know, climate change is an important challenge right now. So the TAIAO project have different components. So maybe we are really based on providing tools for analyzing the data, a platform for organizing and accessing the data, and then how we communicate. So one of the goals is to grow capabilities. So this is something it's very important. In terms of the team, we have many people, many types of people, from PhDs, data scientists, environmental scientists and software engineers. So I think the team is the most important thing, is the thing that we are most proud. So we have many different people, especially here in Auckland. We have Jörg, we have Yun Singh, we have Heitor Gomez in Victoria, we have Barbara Vetrova in Canterbury, and then we have people in Waikato. So I think that the team is what makes this project special. And in terms of how this program benefits New Zealand, so we have different things. So one is delivering excellence. So the idea is that we are really focused on quality, in terms of research, growing capability. So this is something that we do like through running a hackathon and in terms of providing online courses. We are focused on leveraging collaboration and giving effect to the Vision Mataranga. So that was the benefits that these data science projects have. So we have a nice website. So this is the TAIAO community website. The idea is that we want to have data sets and notebooks and discussions on software. The idea is that we're not storing the data, so that we are a catalog of data sets. So we can go there and then we can see all the different data sets that we can use and also the corresponding notebooks. So that's nice because we can see the notebooks in Python that are a good way to understand how these data sets can be used. We have some open source tools. So we have MOA, that was a software in Java for machine learning for data streams. So now we have this River project. This is in Python. It's like MOA, but in Python. And now we have recently Heitor Gomez in Victoria, University of Wellington, started this project. The idea is to be able to have a fast way to do machine learning for data streams in Python using a bridge with Java MOA. And I'll show you later that, we have very interesting results in terms of performance. We have different tools. So we have, for example, the species classifier. So this is a tool that runs on the mobile and is specific design for the species in New Zealand. And the nice thing is that the model is on the mobile, so there's no need of mobile connection. We run the models on the device, and is quite specific for all the species that are in New Zealand, and that has been done with data from iNaturalist that has been providing all of these images that are specific with the species in New Zealand. We have also been collaborating with NVIDIA. The idea was to make Weka much faster. And here, what we did basically is to allow Weka to use the software that NVIDIA has for machine learning, the Rapids toolkit. And what we did is to have this new accelerated Weka that combines both. We have a new software. It's a toolbox for evaluating XI explanation. So one of the issues is that there are many explainable AI methods. So we wanted to have a tool that allow us to evaluate them and compare them. So for that, of course, we need the ground truth. But then from that, we can, with this Python toolkit, we can just compare the different methods. We are also quite interested in data architecture. So we are quite interested on the data mesh architecture. So the idea is that instead of having everything centralized in a data lake, the idea is that we want to be able to manage data in a distributed way. And what we do is that we consider data as a product. So the idea is that every time we want to access data, we are going to have an API. We are going to connect to that. We are going to have ownership of the data. So everyone that is owning a specific data set is going to it's going to have a domain owner. And we, of course, will need a self-serving data platform that is going to coordinate all of these things. And finally, we'll need a federated computational governance. So interesting thing is that this data mesh is a distributed architecture that was created for efficiency reasons. The idea was that when we are dealing with so huge amounts of data, dealing that in a distributed way instead of putting everything in a centralized way seems much more efficient. So this is why many banks or financial entities are using this data architecture, because on real time is really much more efficient. And also it gets that you have people responsible for the data. That helps to, when there are issues, problems, it helps to solve things. So we have been applying this to several projects. So this is the flood impact prediction. The idea is that with Waikato Regional Council and with Met Service, we get data. And then from there, we try to predict when flood is going to happen. So in this case, yeah, we use this data mesh architecture to get data from different places. And we applied this to also the forest flow project. This is a project that basically has some sensors on the forest. And the idea is to, again, try to recollect this data in real time and be able then to do machine learning on trying to predict the moisture of the land. So again, this is a collaboration with Scion, and the idea is the same: is try to use this new data mesh architecture to be able to set up these structures. We have different projects. So this is from Auckland with York and Yunsing. The idea is to use machine learning for detecting algal bloom. Of course, the idea is that the scientists will go to the lake and then they measure, but the problem of that is that it's very, very expensive in terms of time and resources. So the idea is, can we use satellite images to do that? And yeah, this is a very nice work when they were able to use machine learning to detect algal bloom. That is a big issue. And it's creating a lot of environmental problems. So that's our work from Barbara in Canterbury. The idea is to predict marine heat waves. This is a type of events that are happening, and it could be nice to be able to predict them. So in this case, they use graph neural networks to represent all the data and then to try to find these heat waves. So yeah, that was a little bit the explanation of the TAIAO. Of course, there is much more projects. It's a big project. You see there are many people. That was only some of the projects that we are working. Okay, and then finally we have the more how we can do green AI. So the need for that is, again, is the amount of energy that we are using. Still, it's something that is not too big if we compare with the blockchains and cryptocurrencies, but still this is something that is growing, and the main reason is because the models that we are creating are increasing in size, right? So that's so if you look at the number of parameters, we are already thinking that we have trillions of parameters, so that is also something that is going to be increasing. So yeah, that implies that we are going to be using much more energy, so we need to see how we deal with that. Of course, there are many different ways, hardware to software to improving data centers. There are many ways that we can do these green AI. It's not only one way. One way is really algorithmic, trying to improve how we do things. In that case is the standard complexity, right? So in this case, for example, we have computing shelf values for trees. The idea is that if we get an increase on complexity, usually that corresponds to an improvement in terms of energy, right? So this is why all this algorithmic work also is quite important, because if we can create models or algorithms that are similar to the ones existing, but they use less time or less memory, it's a huge improvement. One way of doing green AI, as I said, there are many. So we can focus on hardware, we can focus on data centers, we can focus on improving the efficiency of the methods in terms of complexity. I really like this one, that is the idea is that if we want to have a data set of data and we want to be efficient, so what's the most efficient way to do that is only doing one pass. Because there is no way to do it much more efficient, right? If we start doing passes, that means that we need to store the data, and that's going to take much more complexity. So yeah, so doing only one pass over the data is really, really efficient, but still sometimes that's not enough, right? So we need to still see how we can be much faster or much more efficient. And then we usually like to use these approximate algorithms. The idea is that, okay, we are going to have a small error with high probability. So for example, we can have a small error of 0.1% with probability of 99%, but the algorithm, instead of running in 1 day, is running in seconds. This is a huge improvement. Yes.
You say one pass over the data, but that presupposes that all the data is equally useful and that all of the data are essential. There's a more efficient one which learns only from the data which are going to turn out to have been useful for learning whatever hypothesis that you want to form. So is this, this is all. So what's the status of the? What's your stance with respect to this?
Yes, that's a very good point. So I think that usually we can say that the data could be, or it's already there, right? It's already stored, or the data is being created and is arriving continuously, right? If it's arriving continuously, yeah, that makes sense. What you were saying, maybe we really don't need to do one pass. We don't need. Maybe if we can do something, maybe. If the data is arriving is so big, we need to focus on the one that is really relevant, right? And maybe all the other we can discard.
Maybe it's like each data is subject to the minimum necessary computation to achieve final goal. Because that could be the minimum possible calculation is deciding to use or not use the data.
Yeah. That's a good point. So I think that's the way to make it really efficient, right? So it's like, okay, so yeah, there are different approaches, like for example, active learning on saying, okay, so we have a cost, for example, to ask for labels. So let's see where we spend this money, right? So yeah, that's a good point. So I think that. For example, Amazon has this SageMaker set of tools that when they started this, they started saying, okay, we would like to have very fast machine learning methods. So let's do that doing only one pass. And then they did that. They built the tool doing only one pass. Of course, the problem of doing one pass is that sometimes it's not working, right? Because we need to do, especially in deep learning, right? Only doing one epoch, only doing one iteration, usually is not good enough. But in terms of if we want to be really, really efficient, yeah, it's doing only one pass, and then maybe, yeah, what you were saying, just discarding everything that is not valuable. There's no value on managing that.
Yeah. This suggests an algorithm. Maybe we can talk afterwards.
Yeah, cool. Thanks. So yeah, and sometimes still, for example, if we want to keep we want to use a lot of memory. Sometimes there is a nice, what we call sketches that we can compress the information in. We are going to lose, of course, because we are not keeping all the information, but we can really, really simplify the amount of memory that we are using. So yeah, so streaming machine learning is one approach for that. So the idea is that we are looking only data only once, and yeah, we are going to suppose that we are going to be efficient in terms of time and memory. First, because we are not storing the data, so the memory that we are using may be fixed. And as we are not storing the data, we don't need to revisit the data. So we are going to be very efficient. And another important characteristic is that we can be adaptive. Because one of the things that happened is that we built a model, it's working really, really good at now, it's getting 90% of accuracy, but maybe 1 week later, it's the same model is only getting 10% of accuracy. So how we solve this. So one way is, okay, we need to build models continuously, so corresponds to the current distribution of the data, or we can have these adaptive models that when data is changing, then the model also is changing over time. So for example, if it's a tree, it can replace branches, it can rebuild the tree so that the tree corresponds to the current distribution of the data. So yeah, let me show you an example. So imagine that, yeah, we have 8 bits, okay? So, imagine that we are counting events and we want to store the count of the events that we are seeing. So we have only 8 bits. So what's the largest number that we can do? Of course, this is 256, right? This is the exact number. Now, the thing is, can we do better? Can we store more than that? And in fact, that was the first paper on streaming. That was from Bob Morris at Bell Labs. That paper was counting large numbers of events in small registers. And only using 8 bits, he was able to store 130,000 events. Of course, how he was doing that? So he was doing that storing the logarithm of the number, right? Instead of storing the number, that was this string. So yeah, but this is really something very, very powerful because we can really, really reduce the amount of memory that we need. And in fact, this idea of sketches. So just to finish this, so how this works, that's very, very simple. So every time there is an event and we want to count, so if we want the exact solution for every event, we count 1. So that's the exact solution. If we want to have the approximate solution, what we are going to do is that we are going to, for each event, we are going to add 1 only with probability P. And if we want to store the logarithm of the number, what we need is P to be a power of 2. If P is a power of 2, what we are storing on the counter is going to be the logarithm of the number. So it's very, very simple, but it's going to help us to really use a very small amount of memory. And there are other algorithms like this, that was used at Facebook for computing the degrees of separation. If you know, there was this famous experiment of Milgram that wanted to compute the degrees of separation of people in the US. So the idea was to send letters from one coast of the US to the other and see how many people was needed in the process. And the time was 6. I think that was on the 60s. And then, yeah, this is this famous 6 degrees of separation. So if you want to do it right now, how you do that? So you use Facebook, right? Because you have everybody that is connected. So the nice thing is that at Facebook, with some researchers, they were able to do this computation. So imagine that you need to see everyone, the distance to everyone else. And at Facebook, we are talking about 1 billion of users. So it's really, really a huge amount of computation. So there was 2 times that they did that. So that was in 2016. But the first time that they did that was in 2011. The computation was 4 degrees of separation. And that was done using only 1 machine. And the idea was that they were using these probabilistic methods that were really, really good. And they were able to obtain this. So that's the nice thing of these methods, right? It allows us to do things that, if we want an exact solution, is going to require a lot of energy. Okay, in terms of machine learning, there are methods that are streaming and methods that they are non-streaming. For example, decision tree, you see the decision trees are really good because they are explainable, so we can understand how decisions are made. And when we combine them in samples, are really, really good. The problem of decision trees they are not incremental, they're not streaming. And why? Because every time we need to decide if we split a node or not, we need to see all the examples that corresponds to that node and compute the information gain, and from there decide if we split or not. So the standard decision tree needs to keep all the examples. So how we do that in a streaming scenario where we are not keeping the data? So what we are going to do is, okay, every time we need to decide if we split or not, we're going to wait for new examples to arrive. And because in this case, we are talking about large amounts of data, we only need to wait. So once we have enough data, then we are going to do the split. So now how many examples we need? So for that, we use the holding bound, and this is why these trees are called holding tree. The nice idea of a holding tree is that if we have enough examples, the tree is going to be the same as in the standard scenario. And there are theoretical results that prove that. And it's very simple. So what it's doing is creating the tree, and every time there is a need to decide if we split or not, it's going to use the holding bound to compare the difference between the information gains, and if it's higher than this amount, then it's going to split. So this is why these trees are also called very fast decision trees, because they can be computed in a very, very efficient way. So one thing that we did, of course, these trees are good when they are ensemble, right? So we proposed this adaptive random forest. The idea was to have the advantage of random forest, but in a streaming way. So as you know, a random forest is a combination of bagging and random trees. So in streaming, what we need to do is having adaptive bagging and streaming trees. So streaming random trees. So in this case, we use random holding trees, and then we use a streaming bagging. And also we wanted to make it adaptive. So what we did is that we have some change detectors that they detect when something is changing, and then we need to change the members of the ensemble. The problem of the random forest is that it only works with trees, right? So it could be nice to have something like random forest, but they work with different models. And that's the nice thing of these random patches. So the idea of random patches is like a random forest, but for any model. So what's the meaning of that? The meaning of that is, remember, in random trees, what we do is that every time we decide to split, we use only a random number of the feature, right? For example, we have 100 features. We may use the root square. We may use 10 random features to decide to how we split. And we do that when we build the tree. So the trees are really not good because we do it randomly, right? But the combination is really good. So that's why there is this idea of randomness that works really well for this type of models. So if we look at what we are doing when we are creating these random trees, basically what we are doing is that we are not using all the features. So maybe the solution is, instead of doing that at the level of the node, we can do at the level of the classifier. And then the nice thing is that what we are doing when we are building these random patches is basically we are having the data set, we are removing features, and we are removing instances. And it's a very simple idea, and then we combine like a set of 10, 100 of these classifiers, and it works quite well. So let's say that these random patches is a generalization of random trees to any type of learner. And the interesting thing is that in terms of results, also working with trees, it's really, really good. And it also, in this case, it outperforms a random forest. So it's quite interesting that it's not only more general, also it's much more efficient, much more accurate. Okay, so that was in the part of, in terms of streaming. When we're talking about the streaming, usually we talk about data that is tabular, but nowadays we have a lot of data that is complex data, images, and then we like to use deep learning, right? So then the notion is we call it continual learning. So the idea is that we are going to have a stream of data, of images that is going to be arriving, and then we are going to divide the process into different tasks. And that's there's a huge number of papers on that. So one thing that we did, that was 2 years ago, is that we try to improve how we do this continual learning. So one approach is that we keep like a buffer where we keep the examples, and we use these examples to update the models. So what we did is that we use augmentation to improve the results for these techniques. And finally, just to conclude, I'd like to talk about open source tools. This is something I think it's relevant. So there was this interesting discussion, remember in the 90s, when still at the beginning, everything was not open. So we had, for example, Microsoft, there was the CEO, Steve Ballmer, that was calling Linux a cancer. So now seems quite old, but at the time, yeah, they were really, really fighting against that. But then, yeah, suddenly they changed their mind, and then they become really, really open source friendly. And Microsoft, they bought GitHub, so they are really, really very open source supporters. Unfortunately, last year was this discussion about the large language models, and at that time there was again the discussion about if open source was good or not, and if the open source needs to be banned or not. And in this case was Mustafa Suleyman that was saying that maybe these models are so powerful that needs to be decided by the government who can use this technology or who cannot use it. So there was a period of time that people were discussing again if open source needs to be banned or not. Not if it needs to be used, but if it needs to be banned. So that was really, really, really a strong opinion, right? And at the end, in this case, I think Meta with Jan LeCun, they provide all of these open models, and now we have both, right? We have the closed, we have the open. Everything is fine. So at the University of Waikato, we have in the 90s, they created the Weka software. So that's Auckland created R. So in Waikato was the Weka software that was very popular because it was in Java. And it has also the book data mining. So it was used in many, many universities to teach machine learning. In terms of data streams, we have MOA. This is a software in Java. It's open source. It's similar to Weka. And there are many, many different algorithms. So classification, regression, clustering, outlier detection, frequent pattern mining, active learning. There are many, many different things. It started in 2008, so now it's almost 15 years. So there has been a lot of methods that has been incorporated, and it was very easy to use and extend. And we had this book at MIT Press. That's machine learning for data streams with practical examples in MOA. And that's a book that is open available, so you can read it online. You don't need to buy it. As I said before, the problem right now is that everybody's using Python, right? So MOA was in Java, so people want to run experiments on notebooks, and so that's why we have this project. This is River. So River is the merge of two projects. One that was called GRIM, that was more industrial oriented, and Scikit Multiflow that was more academic. So Scikit Multiflow was created by my PhD student, Jacob Montiel, that now he's at Amazon. And we decided to merge the two projects. So we have a community that is good with practitioners and also with academics. But the main problem with River is that everything is in Python. So it means that it's really not very fast, right? And this is why this year, Heitor Gomez at Wellington, part of the TAIAO project, decided to see it could be nice to have something in Python that has the advantages of MOA in Java, right? So then he thought, okay, so let's create this machine learning library. At the beginning, it's based in MOA, but now it's growing and has a lot of new things that MOA does not have. Especially it can use neural networks and do some continual learning. But the most important thing is that it's really, really fast. So if we compare River, so this is an adaptive random forest ensemble. We think with one data set, we compare River and copy MOA, we see that, River is taking 2 hours and 4 minutes, and MOA is almost 4 minutes, and copy MOA is a little bit more, but not more. So we have the advantages of two things, right? Python and MOA in the same framework. And yeah, I think that's also basically I wanted to talk about green AI as these two aspects. So one is how we use AI to solve sustainable problems, and the second one is how we do AI in a much more efficient way using less energy. I think it's an interesting topic in the sense that there's a lot of people working on that, and it's very exciting to see how things are moving and yeah, how things are. Very excited to see how things are going to be in the next years. Thank you.
Any questions?
Well, as always, so I've been thinking about this AI sustainability consumption problem for a while. And so during the last few of my slides, I asked GPT run. Supposing that AI increases at the rate it has been over the next 10 years, right? And it decided that that was unreasonable, and 30% per year was more reasonable. But suppose that the power consumption associated with increases at that rate, how much additional solar would we have to install to fully account for that increase? And it's 3.6% of the currently planned solar deployment. So this is not a problem, right?
Yeah.
Everyone's going on about it, but it's simply not a problem. Right? You don't have to run the calculations when it's nighttime. It can be done fully renewably.
Yeah.
Right? So why do you think people are making such a big deal of this when it doesn't take long to work out?
Yeah, I think that, yeah, as you were saying, that there are the two extremes, right? So the two sides. So one is saying, no need to worry about that because we are really improving how we are managing data centers, we are improving. So the problem is going to be solved by AI, right? So AI is going to help to improve how we do things. Then there are other people that say, no, this is important, and then we need to see how we need to put a lot of effort on how to minimize the models, make it smaller, use less. I think that for me, maybe the right path is the one in the middle, right? So I think that we should not be too worried because there is a lot of advances, and you were mentioning also.
Just the amount of power just isn't going to be that much, right? Compared to what we're already doing. And for New Zealand, it's an advantage.
Yeah, exactly.
We are in a time zone where we can do the computing.
Yes, yes. Yeah. No, exactly. I think that we are really well positioned for that. And also because the energy here is green, right? So if you compare with Australia, the energy in New Zealand is much greener than in Australia. And I think that, yeah, there is a lot of things that can be done in terms of, renewable energies, with wind, with solar. For me, the interesting thing of this is that, I don't know what you think, but for me, I know what could happen in 6 months, but more than 1 year, things could be really, really different, right? So what I see is that things are changing in all aspects, right? So it could be a new type of energy appears, could be, so maybe all of these problems that we are thinking right now, maybe not so important. But what I think is that we can look at this also as a way of efficiency, AI, right? Efficient AI. So how we want to do AI using the less amount of resources. So in terms, for example, of how much we need to pay, right? If we are paying a cloud solution, if we can do the same thing.
There are many reasons to do it.
Yes.
But the ecological impact reason seems to be a poor one, right? Maybe yes, we can't manufacture GPUs fast enough. So if we're wasting GPU time, right, on doing spurious unnecessary calculations, then that's a bad thing. And generally, if you can make these algorithms more data efficient, you won't waste as much time gathering data. Right? So I mean, there are many reasons to do that. It's just that one people tend to grab, and it seems to me to be I don't know, a misappropriation of the there's really a problem, right, with the environmental impact. If we can use AI, for example, to build solar farms as quickly as possible. If we can use it as a pretext for doing that, we probably get to the end state faster. So saying that it's terrible that we are doing this AI and we should just stop. I mean, this seems like a malpractice almost. Right?
Yes,
because you can easily show that unless its calculations were wrong. I did use O1, so it's
I agree. No, in that sense, I have the same positive opinion as you, right? That we should not stop AI, and we really should. And I also agree that what may be happening is that AI is not part of the problem; it's part of the solution, right? It's going to be really, really helping on how we do this. I think that's this is why when I talk about green AI, I like also the how we help environmental data scientists to do AI, right? Because I think these are the ones that can really help on how to improve things. The other thing is really based on efficiency. So for me, it's very interesting in terms of research. It's very interesting, but I'm not thinking that we need to stop AI. And the people that are saying this, I think it's like the people that were saying that we should stop open models, or AI is really dangerous, or we need to stop doing research on AI.
But that's more likely than that we're going to cause an environmental disaster.
That's another discussion. That's true. Yes.
To my point, you start from the other direction. So most of the people who will be using these tools are actually not computer scientists, expert in the area. So the potential waste of GPU capacity is actually a more significant problem in the short term, I think, in terms of wasted effort, as it were, and wasted resource in a sense, than the ultimate power of the techniques.
I think it's usually for me there are so many applications, right? So there's so many people, and then we see that people are really, really efficient, people that are really not efficient and they are wasting, and then we take the average, and then I see in many applications that people are overusing large language models when they can do it in a much easier way. So that's like a waste of resources, right? But also at the same time, I know that people that are doing amazing things, and they are really, really doing it using a small amount of resources and are very, very efficient. So I think that there is a mix of different ways to do things. But I think it's important at least to know that, right? At least to know that, okay, energy is something. So we can see maybe for business, instead of energy, it's the amount of money that they need to build this or to keep these models. But again, it's a matter of resources, right? And it's good to be resource efficient. Could be in terms of energy, but could be in terms of money, right? Of how much.
Because innovation requires that people play.
Yes.
I think the algorithms are maybe more important because these data efficiency algorithms are very strongly related to algorithms for memory use and for attention and for example, knowledge acquisition, right? So if you can do efficient active learning, that's probably best. Right? And that's optimized in the same sort of way that we're looking to optimize for use of existing data sets.
No, I agree. I think that the algorithmic part is really, really important. And I think it's good that there are many advances on that, because that could make a difference, right? Get it right. Yes.
What do you see as the biggest opportunity for young, computer scientists and entrepreneurs to further their own careers or business ideas, as well as make a positive impact?
So, that's a very personal question. I think it depends on what your personal choices, right? I think that in terms of research, if you look at, or in terms of opportunities, it's always good to be in a topic that is not too big right now, that is going to become successful in some years, and predict that and be there. And then when the topic is really important, then you were there already working on that for many years, right? So that could be the ideal. The problem is that yeah, for that you need to be very smart on choosing the topic, right?
I did that, and where's my paycheck? Where's my payday?
Yeah. Yeah, so that's yeah, I don't know. For example, now quantum is starting, so that's something that is. But again, it's really there are many things that are starting right now. So the problem is what are the ones that are going to be successful, right? It's the and sometimes it's a matter of being lucky and being on the right topic. So this is why for me the most important thing is something that you like and because you're going to spend a lot of hours on that. So it should be something that you are happy to spend a lot of time and energy and if you are lucky, it's good. But if not, at least you enjoy doing it. But yeah, it's quite difficult, I think, to guess what's how the future is going to be, right?
Thank you. That's a good answer.
Thanks.
Focus on what's next. So,
Just mentioned the quantum computer, right? Like, where would you put that? I have no idea about this. Thinking about the energy consumption, are they like at the top or?
Again, the problem with quantum computing is that still we are on the beginning, right? I think right now everything is theoretical, everything is, we don't know if this is going to be a barrier, right? Ideally, you say, yeah, we have this technology, we scale, and then what is happening is amazing, right? But the problem is it possible to scale? Maybe we'll find some physical barriers, maybe we'll find some challenges, and sometimes you can be 99% of the to achieve the goal, but still there is this 1% that is the most important one that is not allowing you to do that. So at the moment, I think everybody is quite excited about that. There's a lot of investment on that. So it seems that that could happen. And of course, yeah, if that works, it's going to change how we do computation and also how we do AI. But yeah, and it's going to be, yeah, the complexity is going to change completely. And then we are going to be able to do computation in a much cheaper way. So that could be one way. But my feeling is that it's really interesting topic of research, and I think it still is research. And I know there's need a lot of money to do it. I know that Australia is investing right on that; they are going for that. So yeah, it's
hard to guess what it will take. It's kind of technically solved, right? Like, in terms of energy, etc.
Very, very low. The end point is very, very low. The current point is really high. You need these really expensive refrigerators and
yeah. So you look at how they are doing research. Basically, now they are simulating with GPUs. So they are working on all the theoretical algorithmic part, but yeah, everything is theoretical because when you do that on
we don't even know if it's going to work, right? We don't know if you can maintain coherence for a computationally meaningful number of bits here. It's looking promising. But,
exactly. And it's not only computational scientists; it's also physicists, and yeah, it's not solved yet. Yeah.
Other questions?
In this program, which bits do you think are most likely to matter? Which bits do you find most exciting, and which bits do you think are most important in our program?
I think that it's a personal thing. For me, the most exciting thing is the fundamental machine learning data part, the one that we publish at machine learning AI conferences. Maybe for me, that's the most exciting. But maybe the one that is going to have more impact, I think, is the one helping environmental scientists on these specific applications. I think this is the one that maybe it's going to be. Yeah, I think if TAIAO should be remembered as this, right? As a a project that was able to help environmental scientists to solve the problem. But for me, the exciting part is that, yeah, it's a combination of fundamental research on AI and also open source tools and this collaboration with environmental scientists that I think this idea that to do AI data science first, what we see is that the data is really not prepared. And that's also something of the challenges that we are finding, and yeah, it could be nice to try to help them on how to do that more, because if not, it's going to be difficult to scale and do large things if the data is not well stored or well managed.
Wondering if there's an application data learning at the data set level, right? So which data, if you could gather a data set, and what size of data set would give you the maximum information gain with respect to solving the problems you want to solve?
Yeah, that's a very interesting one, and especially because there is a cost, right? So until now we were thinking storage is free, we can store everything, but now we are starting to realize, well, storing things has a cost, right? So maybe then, okay, should we store everything, or let's see what we need to store, maybe. And then I think this idea of selecting, sampling, or active learning, or whatever, say, okay, so this is the data that is relevant, and this is useful. We can build a model. If we use this data, we can build good models, but all of this data is really useless. We don't need to keep that because it's not going to be useful. Yeah.
That is pretty much.
Yeah. Yes.
Compared to the old days, so on the size of a disk drive, you can store on one hard drive all of the data storage capacity when we were kids.
Yeah, exactly. Yeah. And then all data was good. Yeah. So someone was telling me about information, right? So, well, it's like food, right? At the beginning, when there's no much food, all food is good, right? But when you have a lot of food, then there's good food and there's no, and it's healthy food, right? So the same is with information data. It's data that is really good and useful, but a lot of data is completely useless.
Okay, so thanks again. See you at the next machine learning seminar.